Okay. Hello, everyone. Let me just see here if I can make sure my video looks right. It looks like it got a little bit smaller, so let me go back to standard and then back to widescreen. Okay. Oh, there doesn't seem to be a Zoom link for today's lecture on Canvas.
Yeah,
Is that right?
that's what I saw. I went ahead
I
and put it
can't
on
hear
the
you,
Slack.
Carl.
Oh, really? Okay.
Try again.
Can you hear me now?
Yeah.
Okay. Yeah, I went ahead and posted it on the Slack channel at the last second.
Interesting. Is it there now on Canvas?
Sorry, it's loading. No, I don't see any lecture meetings still.
Wow, that's really weird. Okay. That's really strange. They all have disappeared. Let's see what we can do here. So let me schedule a new meeting for today. Actually, this is going to be a little bit too complicated. Let's throw up a link for today, for just today. Actually, can you do that, Carl? Can you put that on the web page? Just schedule a meeting, or do I need to have permission to do that?
On the Canvas webpage?
Yeah.
Yeah, it looks like I can edit. Yeah, the syllabus page.
No, not the syllabus page, the Zoom.
Oh.
Okay, so I just tried.
Okay.
But it's probably, no, but it's not the link that we're using now, right? Is the link we're using now
Yeah.
589?
No, this is a different meeting ID.
Okay.
The ID we're using now, I put on the Slack channel. That's where people were asking about it.
Okay, so let me try the course emailer. So can you tell me the meeting ID?
Yeah, sure. Or can you see the chat? Or
let's see here. Yes.
Great.
But now I need to know the rest of the URL.
Oh, okay.
So it's harvard.zoom.us/J. Isn't there a password also?
Yeah, Oxford Street. Sorry, I joined this directly in Zoom. I don't have a URL. Okay.
Oxford Street. Okay. Let's try this. Okay, we seem to be up to 16 people. Let me ask, Catherine, can you tell me if you were able to get in, which evidently you were, and how?
I got in with the meeting ID that Carl posted on Slack.
Okay. Let me just see if I just posted a URL to the Canvas email as well. I can't seem to load that. Can you check if that works as well, Carl?
Yep. Yes, looks good.
Okay. Okay. Well, we have 16 people. I hope that's, I do not, this, I was invited to a conference in Heidelberg over the weekend, and I have a feeling that they took my email address and assigned it to a different Zoom account. All my Zooms were canceled or something. Anyway, thank you for coming. I hope more people join us. So any questions before we get started today? So my goal for this week is to talk about what's called Hopf's argument, or ergodicity of hyperbolic automorphism on the 2 torus. And this is really one of the main arguments in ergodic theory that will allow us to do ergodic theory in hyperbolic surfaces. So please chime in. We're a small group right now, so I welcome interruptions. So let me remind you what our new setting is. Oh, and hang on a sec. Let me just see if I can move my gallery view over here. Okay. Let's see. So, can everyone hear me? Can you raise your hand? Okay, thank you. It's very quiet suddenly. So our setting now is topological dynamics, and we're going to add in measure theory considerations. So we have X, which is a compact metric space. We're not going to use the metric on X. It's just to give it a little bit of topological tameness. This implies, for example, that X is separable. That is, it has a countable dense set, and that the Banach space of continuous functions on X is separable. And that will later imply that the space of probability measures on X is separable. Is not just separable, but it's metrizable. So let me just remind you that the space of probability measures is a subset of the dual of X, which can be thought of as the space of signed measures on X. And I will often write the pairing between a function and a measure by either the integral over X of f with respect to mu, that's sort of the more standard notation, but also, after all, these are linear functions on C of X, and so you can also just write this as mu of f, the measure evaluated on f. And then the space of probability measures is convex, and it's also compact in this topology. And it's the closed convex hull of its extreme points. These turn out to be general features of compact convex sets in locally convex topological vector spaces. They're general theorems of functional analysis. What is but when I say it's compact, we have to say what the topology is. It's the so-called weak star topology. And in this topology, mu n tends to mu if and only if mu n of f tends to mu f for all continuous functions. And in fact, since the space of continuous functions has a countable dense set, which comes from the fact that X is metrizable, you only need to test convergence on countably many f. And you might worry, oh, is this some weird topology where I can't use sequences to describe convergence? But in fact, because of this assumption, P of F is convex, compact, and also metrizable. It's a pretty tame space. And the way you should think of this space is that somehow it has a copy of X inside it, corresponding to the delta functions at each point. And then everything else is a convex linear combination of the points of X. So basically what we've done is we've taken X and we've made it into a space where you can take averages of points in X, and those averages are measures. So when you apply them to a function, they average the function over those finite sets, and then you take limits of these objects, and that's what the general measures on X look like. Okay, now what about extreme points? What are the extreme points? So a typical convex set you might visualize as being a polygon of some type in, say, in R3, and the extreme points are morally its vertices. But to give a precise definition, an extreme point is a point that does not lie in the interior of an interval contained in the compact set K. So if we have K, and we want to show that a point's not extreme, then we just have to find an open interval around it like this. On the other hand, this point is extreme. You can find a half open interval that contains it, but it doesn't lie in the interior of an interval contained in your compact set K. Suppose I were to draw the backwards letter D and fill it in. What are the extreme points of this convex set? Anyone?
The semicircle thing on the left hand.
Okay. And what about these two endpoints? Are they extreme?
Yes, they are as well.
Okay, good. And what about this line here?
No, it's not.
Right. So if you were to pick a point in the interior of this line, you could slide it backwards and forth, staying inside the set. So it's not an extreme point. Okay, so now let's think of the measures, a probability measure on our space, and ask, when is it an extreme point? Well, if this probability measure can be written as a non-trivial linear combination of two other measures, then you can slide it towards one measure or slide it towards the other. And so it's not an extreme point. And you can always do that if there's some mass in one part of the space and some mass in another part of the space. So the only probability measures that are extreme are the delta masses on X. So the extreme points give a map of X into the space of probability measures, sending a point X to the delta mass there, and the image is equal to the extreme points. That's a little exercise. And now there's a nice theorem in terms, in general functional analysis, that says that a compact convex set is the closed convex hull of its extreme points. So when we're looking at more general convex sets, you might say, how do I even know they have extreme points? And in fact, the construction of a extreme point in general requires the axiom of choice. But admitting the axiom of choice, there's so many extreme points that the smallest convex set that contains the extreme points is the space you started with. That's what it means to say you can reconstruct the set from its extreme points by forming its closed convex hull. That's a feature of any compact convex set in a reasonable space, like a Banach space or a more general locally convex topological vector space. Whose theorem is that? Can somebody attach a name to that theorem? Somebody sit in on 212A with me last year? I'll give you a clue. The initials are KM.
Is it Krein-Milman?
Yes. So this fact is called the Krein-Milman theorem. I mean, the general principle that underlies it. And this compactness is what's called Alé-Agu's theorem. But I want to mention that in this setting that we're talking about, Krein-Milman is subtle, but Alé-Agu's theorem is not. It's pretty easy to show the space of probability measures is compact. And the reason is that so here's a little proof that P of X is compact. Remember, this is in this weak star topology. So we choose Fn in C of X, which are dense in the uniform topology. As I mentioned, this space is separable, so we can do that. And then when we're given a sequence of probability measures with their total variation less than or equal to 1, or so let's say these are probability measures, then we know, of course, that the mu and n of f is an absolute value less than or equal to the supernorm of f. Because this has total mass 1, it's just an average of the values of f. So these numbers are bounded. If you fix a particular n, sorry, let me put a different index in here, k, these numbers are bounded. In fact, let's just look at this at the first function in our sequence. So these numbers are bounded, so you can pass to a subsequence so that these converge. Okay, and then you pass to a subsequence so that mu n 2 of f, mu n of f2 converges, then the mu n of f3 converges, and then you diagonalize and you get a subsequence such that q n k of fi tends to some limit li for all I. And then you just define, there is a unique new measure now whose measure on fi is given by this limit function li. And so that's how you prove compactness of the space of measures. But as I mentioned last time, it's also should be intuitively obvious that this compact space, you have this finite amount of sand, and the different ways you can spread it out in the space form a compact set of configurations. Okay, so that's the basic setting. And now we introduce a continuous map from X to X. And just like in the case of measure-preserving transformations, it's nice sometimes to imagine T is invertible, that it's a homeomorphism, but the general theory works for continuous maps just as well. Occasionally a little nuance has to be brought in. And now here's the important thing about measures and continuous maps. In general, if you had a continuous map from X to Y, it would give rise to a map from the continuous functions on Y to the continuous functions on X. Because if you add a function here to the real numbers, then you could compose and get a new function here, f composed with T. And so dualizing, you get a map from the measures on X to the measures on Y. And this map is usually denoted by T lower star. It's called the push forward of measures. And the measure is defined concretely by T lower star of mu, evaluated on a set in Y, say an open set U, is just mu of T inverse of U. And since T is continuous, this is also open. In particular, it's a Borel set that defines the push forward on all the open sets, and then it extends to the sigma algebra they generate. That's the definition of the push forward measure. Okay, so measures push forward, and this map that sends the measures on X to the measures on Y is, as you might expect, it's continuous in the weak star topology. So in particular, if we have a map from X to itself, we can take a measure and push it forward, and maybe we get the same measure. The total mass of the measure is preserved because of this condition, but maybe it's actually the same measure on the nose. So we let Px super t be the set of probability measures mu on x such that t lower star f is equal to t lower star mu is equal to mu. And that's the same thing as saying that the integral of f composed with t with respect to mu is the integral of f mu for all continuous functions f. Those are the invariant probability measures for this transformation. So at the beginning of ergodic theory, we said, oh, let's just posit that we have an invariant measure. From this topological perspective, we say, well, let's just start with a homeomorphism or a continuous map and try to find invariant measures. Let's try to examine this set of x of t. And a couple of things are fairly obvious. This set, for example, is this is certainly closed. It's compact because it's sitting inside all the probability measures, and it's convex. But is it non-empty? And so perhaps the first theorem in topological dynamics is that there always exists at least one t-invariant measure. So theorem is provided that x is non-empty, px of t is non-empty. And for the proof, we use the fact that x is non-empty to pick a point in it. And then we consider the orbit xi, which is pi of x. So we start moving this point around. 0 maps to x1, maps to x2, etc. And now, given a function, we can average the function over not the whole orbit, but a long initial piece of the orbit. So we let mu n be 1 over n times the sum of delta masses at xi, going from 0 to n minus 1. So mu n of f is just the average from 0 to n minus 1 of f evaluated at the points xi.
Are you in?
Yeah. Was there a question, comment? No? Thanks. Okay. And now here's the great thing about mu n. Mu n is not an invariant measure, but it's pretty close. Because if you take mu n of f composed with t, mu n of f composed with t, what is that? That is going to be the average of f composed with t over x naught up to xn plus 1. So that's the average now, not from 0 to n minus 1. So it's the average from 0 to n minus 1 of f composed with t of xi. But that's just the average from 1 to n itself of f at xi. So when you change f to f composed with t, you lose this point, and then you gain one new point to average over. But remember, x is bounded. So when you change from f to f composed with t, you only change this average by something that's bounded by the sup norm of f divided by the number of points in the orbit. In other words, this measured mu n is almost invariant in the sense that mu n of f composed with t minus mu n of f for any fixed f is less than or equal to 2 over n times the sup norm of f. And this goes to 0 as n goes to infinity. So these functions, these measures are becoming more and more nearly invariant. And now you just pass to a convergent subsequence. Pass to a convergent subsequence. Mu n sub k tends to mu. Well, maybe I'll call it mu. And then since this is becoming more and more nearly an equality, in the limit, you actually get equality. And then nu is an invariant measure. So then nu is in px of z. Okay, now, what was the key to making this proof work? This proof actually relates back to the expansion properties of graphs that we discussed way at the beginning of the course. What makes this proof work is it works because the integers are an amenable group. And what that means is that their Cayley graph is not an expander. As we saw at the very beginning, if you take a bunch of consecutive points, say from 0 up to n minus 1 in the integers, we call that set A. You connect them when they differ by addition of 1, the generator of Z. Then the boundary of A, the things you get to when you apply plus or minus 1 to A that you didn't have originally, just consists of 2 points. So A is much bigger than the boundary of A, and that's why this average is almost the same when you move A back and forth. In other words, the fact that the integers have an almost invariant set allows us to construct measures that are almost invariant. So indeed, the same proof works not just for the integers, but for any action of an amenable group. And so it also works for example, z to the d is also okay. If you think of the real numbers in the right way, you can also construct invariant measures here. So one thing I want to just make you aware of, to sort of broaden one's horizon, is that there exist group actions on compact metric spaces that do not have any invariant measures. So this theorem is actually special to the fact that we're working with this rather simple kind of group. So here's an example. Here's one of my favorite group actions. Take SL2Z acting by Mobius transformations on the real numbers union infinity. So that's a topological action of fractional linear transformations on the boundary of the upper half plane. And then the theorem is that if you take the probabilities on measures on the circle and you try to look for some that are invariant under the action of this group, you get the empty set. Okay, so let's think, for example, about why that might be the case. So you're supposed to have a measure that's invariant under the action of SL2Z. What's a typical element of SL2Z other than the identity? Well, a nice element here is, say, the matrix 1, 1, 0, 1. And remember, in general, A, B, C, D corresponds to the Mobius transformation AX plus B over CX plus D, acting on the real axis. So this corresponds to the map X goes to X plus 1. So if we had a probability measure that was invariant under SL2Z, in particular, when we looked at its values on the real line, we get a probability measure that's invariant under X goes to X plus 1. Well, it might not be a probability measure because there might be some mass at infinity, but it would still be a finite measure that's invariant under X goes to X plus 1. But there is no such measure, right? Why is that? It's because whatever the measure is of 0, 1, if we have a measure that's invariant under translation by 1, that would have to be the same as the measure A plus 1. And that would have to be the same as the measure of A plus 2. And that would have to be the same as the measure of A minus 1. So the measure of the real line, which would have to be finite, would be an upper bound for the sum of the measures of A plus I, but these would all have to be the same. So that would be the infinite sum of the measures of A. And since those are all the same and the answer is finite, this implies the measure of A is 0. Okay, so the only possibility for an SL2Z invariant measure on the boundary of the upper half plane on R bar would be a delta mass concentrated at the point at infinity. Now, what's wrong with that? Well, there's another transformation in this group, 0, 1, minus 1, 0, which just acts by z goes to minus 1 over z. So this invariant measure, which we've just discovered would have to be a delta mass at 0, is also invariant under this transformation. Where does infinity go under this transformation?
To 0.
To 0. 1 over infinity is 0. And so if we had a delta mass at infinity, we would get a delta mass at 0, and then we get a delta mass at all the integers again, and that would contradict the fact that the measure is finite. So indeed, when you take a big group like SL2Z, there are no invariant measures for its standard action on R bar. That doesn't mean we can't analyze the group SL2Z, and that measure theory isn't very important in that analysis. It just means that it won't enter in the naive discussion of invariant measures, let's say, on the circle. Okay. So let's go back to Krein-Milman. So we have this non-empty space of invariant measures. We just constructed one. Who knows, maybe it was in here. So there's some measure that exists. But Krein-Milman ensures us that there are lots of extreme points to this set. An extreme point is a place where there's a supporting hyperplane, and the extreme point is not in the interior of the intersection of the supporting hyperplane with the point. So there's lots of extreme measures, mu as well. This was one that we initially constructed by averaging. And in fact, it's an easy exercise to show that mu in PXT is an extreme point if and only if mu is ergodic. Now, of course, we're changing measures all over the place as we're doing this discussion. So what does it mean for a particular measure to be ergodic? Well, again, it's the usual thing. It says that if we somehow write X as the disjoint union of A and B, these are, say, Borel sets, so they can be measured by any measure we're interested in. And if these are also T invariant, then the measure of A is 0, or the measure of B is equal to 0. And you can kind of see why you might expect this to be true, because if you had a non-ergodic measure, if mu could be split up into a part that lives on A and a part that lives on B, well, then we could take the part that lives on A and rescale it to get another probability measure. And since A is T invariant, that would be inside of our space of invariant measures. And then we could take the part that lives on B and rescale it. So it's a probability measure. Call that mu restricted to B. And then we could put them together, and we could just write mu itself as mu of A times mu A plus mu of B times mu B. And then if A and B both have positive measure, we've written it in a non-trivial way as a linear combination. So the point we started with was not extreme. And so conversely, if it is extreme, it turns out to be ergodic. Okay. So with our new perspective, we should revisit some of our old examples, and we ask a new question, which is, what does the space of probability measures look like? Or what elements can we find inside the space of probability measures? So let me start with a very sort of combinatorial, very basic example that illustrates a lot. So the first example will be Z mod n to the Z. So this is the space of sequences a minus 1, a 0, a 1, etc., where each AI is an element of Z mod n, just one of finitely many numbers. The group structure is not very important here. And then T will be the shift map. So T of AI will be the sequence AI plus 1, where you slide the sequence along by 1. And then we can ask, what does, so this was X. And this is given, by the way, the product, the Tikhonov product topology, which makes it compact, because each Z mod n is compact. It's also metrizable, because it's a countable product. So what's in Px of T? Well, one thing that's in Pxt is what I'll call the coin flipping measure. Namely, you just choose a number between 0 and n minus 1 at random for each of the coordinates, and you do so independently for all the coordinates. And that measure clearly is invariant under the action of T. More generally, if we take any measure on Z mod n, and there's a finite simplex of probability measures there, then we can just take its infinite product, and that will give us an invariant measure for the shift. So this contains the space of all probability measures on Z mod n by taking a measure here and sending it to the product over all Z of the same measure. So this is sort of the independent coin flipping measure. All the coins are identical. When you flip them, they have no influence on one another, and they have n sides. You record which sides come up. Okay, so that shows that this space is rather big. And somewhat amazingly, these coin flipping measures turn out to be ergodic. So they're actually extreme points. But what are some other measures on this space? Well, another nice way to construct measures is to observe that T has lots of fixed points on this space. And in fact, it has lots of periodic points. So how many fixed points does T have on this huge product space? How many sequences are invariant under the shift?
N of them?
Yeah, there's just n. Once you say what the middle coordinate is, all the rest of the coordinates have to be the same. So we'll notice that T has n fixed points. And if you have a fixed point, you can always put a delta mass there. And so delta on the sequence 0, 0, 0 in all directions is also a shift invariant measure, as it is for make all the coordinates equal to some fixed number I. But T also has lots of periodic points. Because if you take any sequence you like, say 0, 1, 1, 0, 1, then you just repeat it again, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, and that gives you a bi-infinite sequence. And this sequence was of, the initial sequence is of length 6, and it doesn't look like itself until you shift it at 6 along. So this gives a periodic point, period 6. And now we can just take these 6 points and put equal delta masses on them. And since those points are permuted by the action of T, that gives another invariant measure. So every periodic cycle gives an invariant probability measure, and indeed it gives another ergodic probability measure. So there's tons of ergodic probability measures here. So you might start to think, maybe all the probability measures are ergodic. But of course, that's not true, because if you were to take two different periodic cycles and put some mass on one and some mass on the other, then the result wouldn't be ergodic. It would have these two invariant sets. However, there do seem to be an awful lot of them. This is to give you some idea of the richness. There are these diffuse invariant measures, easy to construct by taking products. And then also, every periodic cycle gives rise to discrete invariant measures. And if it's a transitive cycle, then that measure is also ergodic. So lots of invariant measures, lots of extreme points. Let's look at another example that I like. Let's look at the map T of Z is, well, let's say T of X is 2X mod 1 on X, which is R mod Z. So the doubling map on the circle. Now this map is continuous, but it's not a homeomorphism, unlike this map. So it's nice to have at least one example like that. And what can we find in TXT? Well, as we argued when we first introduced some examples of measure preserving maps, the usual measure, Lebesgue measure on the circle, is invariant. Basically because if you take an interval on the circle and you take its preimage under this doubling map, you'll get two intervals, but they'll each be of half the length of the interval that you started with. They'll actually be opposite one another. Draw them so it looks more like that. So the length of this interval is actually the sum of the lengths of these two intervals. So the measure is preserved under the inverse map, which is the same thing as saying it's preserved under push forward. So this measure has the property that T lower star M is equal to M. So it belongs to this space of invariant measures. And then again, there are lots of periodic cycles for this map. So a famous one, which is related to complex dynamics, is 1/7 doubles to 2/7, which doubles to 4/7, which then doubles to 8/7, which is 1/7. So again, lots of periodic points, delta masses at each of these things sum up to give you another measure. And by the way, this measure is ergodic, and so is this measure. There's another way here to see that there's lots of invariant measures. Namely, X is a group. And what we're doing is we're taking an endomorphism of this group. So T respects the group structure. T of X plus Y is T of X plus T of Y. It's a surjective homomorphism of the group to itself. And because of this, if you take a point in the group that's torsion, that is, when you add it to itself n times, you get 0, then its image under this map will also be torsion because of this law. So since T is a group endomorphism, we observe that if we let Xn, now realizing that X is a group, be the set of points in X such that Nx is equal to 0, which in this group means it's equal to 0 mod 1, then T sends this set into itself. And so there's lots of finite sets which are sent into themselves by T. Whenever you have a finite set sent into itself, there must be a periodic cycle, and those periodic cycles give rise to invariant measures. Okay. Now this example is actually not very different from this example. The topology is different, and that makes a little bit of difference since we are discussing topology. But notice that if I write a number out in base 2, x1, x2, x3, etc., a number between 0 and 1, and then I double it, all I do is I get rid of this first digit here, and I and I scoot the other digits over by 1. So this is 0.x2, x3, etc. So this map is actually almost the same as the shift on z mod 2, but it's not z mod 2 to the z now, it's z mod 2 to the n. It's the what's called the one-sided 2 shift. It loses information when you shift. Okay, so now for our third example, I want to remind you of T in SL2Z or GL2Z, hyperbolic. So none of its eigenvalues are roots of unity. No eigenvalue is a root of 1. And of course, what this really means is that there's 2 real eigenvalues, and one is the reciprocal of the other. The eigenvalues are lambda and 1 over lambda, where the absolute value of the first one is say greater than 1. And our space X is the 2 torus again. And so here we know that area on the 2 torus is invariant because the determinant here is 1. So Px of t contains the area form. Let me call it dx dy on x. And in fact, this is an ergodic measure. So we proved using characters. But then it also contains measures on the points of order n, because once again, the torus is a group, and sprinkled throughout the torus is the discrete set of points of order n. They're points that have n in their denominators. They have rational coordinates with denominator n. And these finite sets are actually permuted by the action of t, since t is invertible. So they must contain periodic cycles. And we can take such periodic cycles to make lots of invariant measures besides this obvious ergodic one. Okay. Now there's something similar about all of these examples, and rather than trying to axiomatize what it is, let me just tell you some of its features. All of these examples exhibit what's called in dynamics some kind of hyperbolicity. And one of the features is that ergodic measures are dense in the invariant measures for these maps. So you might not think that that's possible. You might think, you know, extreme points, what are these extreme points doing? Don't they have to be far away from the middle of the space of measures? But they don't. In fact, this space has no interior, and the closure of its extreme points is the space itself. Not only that, but let's think about this ergodic measure here. We know that the area form is ergodic for this transformation. Suppose you pick a point at random on the torus and you start iterating it. You look at its orbit. Well, by ergodicity, this orbit spreads out evenly over the surface. If you take a very long orbit, then the delta masses on that orbit are very close to this measure, this area measure. But now it turns out you can perturb the orbit just a little bit and make it periodic. So in fact, this measure is in the closure of the measures of this type that are just supported on periodic cycles. And that's again a general feature of hyperbolicity. In fact, ergodic measures supported on periodic cycles are dense in the space of all invariant measures. So that's true in all three of these situations. In some sense, all of the measures are just limits of the measures permuting finite sets of points around cyclically. Okay, so that's to give you at least a feel for how the space of all invariant measures looks in these three dynamical systems. It's very rich, and part of its richness comes from all these measures with finite support, but then there are also continuous measures in each of these settings, which are ergodic as well. Okay, so that's one side of the coin. That's called this is sort of the hyperbolic paradigm. And now I want to shift gears and talk about what might be called the parabolic paradigm. But I won't push that terminology. Let's just say, look, this is going to be night and day. We're going to look at another dynamical system, and it's going to be totally different. So this is our fourth example, but it's something totally new from the perspective of measures. And this will be our map T of x is x plus alpha mod 1. Again, on the circle. Where alpha is irrational. So this map has infinite order. And as we've seen, this map is ergodic. And of course, it leaves invariant length measure on the circle, or if you like, Haar measure on this group. In fact, that is the only invariant measure for this map. So Px of t, in this case, is 1 point. It is, namely, it's the measure Px. If you like, its Haar measure on S1. Or Lebesgue, the rotationally invariant Lebesgue measure on S1 scaled, so it's a probability measure. Radically different. Now you might suspect it might be different because since T is completely non-periodic, there are no periodic measures to throw into the mix. So there's no obvious invariant measures besides this one. But it's a very strong fact that that turns out to be the only one. When this obtains, we say that T is uniquely ergodic. It only has one invariant measure. Okay, so this is a very powerful property. And one thing I want to emphasize, it's easy to get confused when we're talking about ergodicity mixing and unique ergodicity to think that unique ergodicity is a property of a measure. Unique ergodicity is actually a topological property. We need to have a topology on X before we can talk about unique ergodicity, because without a topology, we can't even describe what the space of all probability measures on X is. So this is a topological property of the pair Tx. We start with a topological dynamical system, and then this dynamical system, by general principles, has an invariant measure, but what makes it truly rigid is that there's only one measure that's compatible with the dynamics. Okay, so maybe we should, why don't we give a proof of this? So one way to do the proof is the following. So C of x is just C of the circle. And C of the circle contains, so I'm going to change my notation of my dynamics just a little bit. I'm going to let the circle be the set of complex numbers of absolute value 1, and I'm going to let T of z be lambda z. So if you like, lambda is e to the 2 pi I alpha. Anyway, I'm just changing coordinates, and the main point is that lambda is not a root of 1, not a root of unity. So we're doing an irrational rotation of the circle in the complex plane. 1, 1 goes to lambda, goes to lambda squared, etc. And I changed to these coordinates because I like to use Fourier series, but I'm not going to use Fourier series in a very sophisticated way. I'm going to say within this space of the circle, we have what I'm going to call the Laurent polynomials on the circle. And what these are finite sums from minus n to n of some complex number times z to the n. Okay, now what can I say about this subspace of the continuous functions? Well, actually, it's much more than just a subspace. It's closed under multiplication. If you take the product of two of these series, you just get a series which still involves only finitely many powers of z. So this is an algebra. It's a subalgebra of the space of continuous functions. It's closed under multiplication. And not only that, if we take a function f in here, remember that on the unit circle, z bar is just 1 over z. So if f is in this algebra, then f bar is in the algebra as well. F bar would just be the sum of a n bar z to the minus n, which is of the same form as the elements of z. So we have a subalgebra of the circle, and it's closed under complex conjugation. I claim that it's dense in the space of all continuous functions on the circle. What do I have to, what theorem can I quote to prove that?
Stone-Weierstrass?
Yeah, that's right. So that's our third general functional analysis theorem I'm using today. So we had Allioglu, we have Krein-Milman, and now Stone-Weierstrass. All three of these are used all the time as tools in ergodic theory. The Stone-Weierstrass theorem says if you have an algebra with identity, and of course this contains the constant function 1, that's closed under complex conjugation and separates points, that is, for any 2 points, there's a function that differs at those 2 points, then it's dense in the space of all continuous functions. And of course, we have a function here which separates points, namely the function z itself. Z gives an injective map from the circle into the complex plane. So by the Stone-Weierstrass theorem, L of S1 bar is equal to C of S1. These Laurent polynomials are dense. Okay, so now let's see what we can say about an invariant measure. We're almost done with the proof of this important theorem that T is uniquely ergodic. So suppose mu is a probability measure on the circle that's invariant under this irrational rotation. Okay, well then, mu of f composed with t has to equal mu of f for all f. That's the definition of invariance. So what can we say about mu of the function, let's let fk of z be z to the k. So mu of fk composed with t should be the same as mu of fk. But what is fk composed with t? It just means we replace z by lambda z, and so we get lambda to the k, z to the k. In other words, these functions, as we've seen before, they're eigenfunctions for the action of t. So this is just mu of lambda to the k times fk. And since mu is linear, this is lambda to the k, mu of fk. And that has to be equal to mu of fk. It has to not change. So the only possibility is that lambda to the k is equal to 1. But, or mu of fk is equal to 0. But the only time lambda to the k is equal to 1 is when k is 0. So what we conclude from this is that mu of f0, which is mu of the constants, that's equal to 1 because we have a probability measure. And then mu of fk is equal to 0 for k not equal to 0. So if we have an invariant measure, we know what its values are on these basic Fourier functions. In particular, we know what its values are on this algebra L of S1 because it kills all of the terms in the Fourier series except for the coefficient of z to the 0. So L of S1 gets mapped by mu to the coefficient A0. And what is A0? It's just the average over the circle of F with respect to Lebesgue measure. So in other words, any invariant measure agrees with the unique measure we think it should be on this dense set. But a measure is a continuous linear functional on C of S1. So once you know its values on a dense set, you know it everywhere. So since mu agrees with the measure coming from Lebesgue measure on the S1 on the Laurent polynomials, it must actually be just ordinary Lebesgue measure on the circle. So, so this implies that mu is equal to the measure, we'll call it absolute value dc by the usual probability Lebesgue measure on the circle. Okay, and that proves that the irrational rotation is uniquely ergodic. It only has one invariant measure. I should say that this proof goes back to Hermann Weyl, and there were many other people who observed this fact. But Weyl really drew attention to the connection with harmonic analysis and the general issue of equidistribution of sequences of points on the circle. So let me amplify this discussion a little bit. So it would be nice to have a proof which wasn't quite so clever. Even though this is very down to earth, if you hadn't thought of, oh yeah, I can use Stone-Weierstrass, it might have been tricky. So let me give you another proof of this theorem. In fact, let's do a more general theorem about unique ergodicity. So what was the key component here? The key component was that we were working on the circle. The circle is a compact topological group. So more generally, let G be a compact topological group and define T from G to G by T of X is, let's say, G times X. Now, not every, turns out compact topological groups admit an invariant measure, just like the circle. We have Haar measure here. So, T leaves Haar measure invariant. We normalize it to have mass 1. It's a nice probability measure. And then the theorem is that T is uniquely ergodic if and only if, when you take the cyclic group generated by Z, and then you take its closure using the topology on G, you get the whole group. So in other words, if and only if the one parameter, the cyclic group generated by Z is dense in this topological group. So in the case where G is a circle, if you take a point on the circle and you take the group it generates and form its closure, it's either a finite group or it's everything. In the finite case, the element had finite order. That's when T is just a periodic transformation. So aside from that, you have to have a unique ergodicity. And of course, the unique invariant measure is Haar measure. But the proof of this is very slick, very fast, and doesn't use harmonic analysis. Even though we have Pontryagin duality and so on available, I'm not going to use it. Let's just observe the following. That if mu is invariant under G, then it's invariant under all the powers of G. because those are just the iterates of T. So if mu is G invariant, then is T invariant. This implies it's G invariant. But the set of transformations, elements of the group that leave this measure invariant is closed. And so once it's G invariant, it's H invariant. It can pass to limits of powers of G. And if H equals G, then this implies it's G invariant. And there is only one G invariant measure on this group. And so that implies that mu is a Hart measure. And therefore we have unique ergodicity. And by the way, along the way, when you'll notice that this group is abelian. So when you have unique ergodicity, this group was always, I didn't require G was abelian from the beginning, but if it's the closure of a cyclic group, then of course it's abelian because this group is. So what about if H is not equal to G? Well, if H is not equal to G, here's my picture of G. It has this subgroup H, and it has the identity G, G squared in it, and so on. So T leaves invariant this subgroup. And so T has an invariant measure on this subgroup H. But if H is a proper subgroup of G, then I can find another coset, GH, which is disjoint from this. Usually you can find infinitely many of them, but in any case, as long as they're different, there's at least one. And then T also leaves this compact set invariant. So there's an invariant measure here and an invariant measure here. Obviously, they're mutually singular. They're not the same measure, and therefore, T is not uniquely ergodic. Okay, so that's another proof of unique ergodicity. Okay, so now let me just change the language a little bit just to, allow some fluidity of discussion and let you understand other questions of a similar ilk you might hear. So in general, if we're given a finite and countable sequence of points, X, we say this sequence is uniformly distributed. Then there should be some measure in the background, so let's state it explicitly with respect to some probability measure mu. If what happens? Well, we form the usual sums, averages for a continuous function, but we don't have any dynamics. We just add them up over the first n points in the sequence. So we take 1 over n, the sum from 0 to n minus 1, f of xi. And uniform distribution means that these sums converge, say pointwise, to the integral of f with respect to mu as n goes to infinity. So another way to say Weil's original theorem is the following. If x in R mod z is irrational, then this implies the sequence nx, those are our x sub n's, are uniformly distributed. It's just a different terminology. We can also state the ergodic theorem, the pointwise ergodic theorem, in the following way. The pointwise ergodic theorem says that if mu is ergodic, then this implies that almost every orbit of T is uniformly distributed with respect to mu. It is also spread evenly over the space with statistics governed by this measure. And finally, we can say what unique ergodicity means. unique ergodicity just means that in the ergodic theorem, you can get rid of this AE statement. So unique ergodicity just means that every orbit of T is uniformly distributed with respect to the given measure mu. And so you see there's a big difference in the ambitions of these two theorems. So when Poincare was studying celestial mechanics, he said, well, I want to understand the long-term behavior of the solar system. And of course, it might be that somehow there gets to be some synchrony between the orbits of Mars and Venus, and Mars starts to oscillate, and then it collides with the Earth. And then, you know, all bets are off. You don't have a theorem about long-term stability of the solar system. But that happens with measure 0, so we can ignore that. But the ambition, when one studies uniquely ergodic systems, is much stronger. We try to understand the behavior of every orbit. We don't throw out sets of measure 0. And up until maybe 30 years ago, it was widely believed that there would be very few circumstances, mostly of not much interest, where one could analyze the behavior of every orbit. You always have to throw out some exceptions. But in fact, and this is a theme we're going to develop as we approach hyperbolic surfaces, the work of Marina Ratner, confirming some conjectures of Raghunathan, show that that is not such an ambitious thing. There's certain kinds of dynamical systems where one can actually obtain unique ergodicity and analyze the behavior of every orbit. And that was sort of a big breakthrough and a shift in our perspective on what could possibly be done in dynamics. Okay, so now let me ask a naive question. So here's a theorem. Let U contained in S1 be an open set, and xn equals nx mod 1, the orbit of an irrational rotation. So one of these uniformly distributed sets. And then I could look at the number of n less than or equal to capital N, such that xn is in U, and divide by capital N. And that's basically the same as taking this sum, Sn, of x equals 0, and evaluating it for the indicator function of U. And then the theorem is that this converges to the integral of the indicator function of U, which is just the measure of U. Okay, so if you have an open set on the circle, and you have this irrational rotation, this orbit spends about as much time as this open set as you would have expected. Okay, the problem with this theorem is that it's false. It sounds pretty plausible, but it's just wrong. So why is it wrong? I see a hand coming up. If I give you this orbit X, can you construct an open set U for which this fails? So let's see a raising of hands for people who think they can imagine a U for which this fails. Okay. Oh, Yan Chang wants to jump in the water. Anyone else? Okay, so since we're already slightly past time, although we did have a technical glitch at the beginning, I think rather than discussing the nuances behind this example I'll just leave it at that and ask you to fix the theorem. And so fixing the theorem involves two things. One is you have to give an example to show this theorem is just wrong. And secondly, you have to change the hypothesis so that it becomes correct. And just as a hint, I'll remind you of something, which is that the measure of the rational numbers is equal to 0. And what does it mean by the measure of the rational numbers being equal to 0? It means there exists an open set U containing all of the rational numbers such that the measure of U is as small as you want. And that should be a hint about how you might make a U here where the theorem fails. It would be a little more exotic than just an open interval. It would be something like one of these open sets you use to cover the rational numbers. Okay, so we'll return to this nuance of unique ergodicity next time, and then proceed to the Hopf argument on toral automorphisms and their ergodicity. Okay, so as usual, I'll keep the Zoom room open, and I will fix the Zoom links for the future. Thank you for bearing with me.
Thank you, Professor.